Hi, this is the last video in this series about consistency models achievable in leader-follower replication scheme. My name is Ivan Fedianin, I am software architect, and in this video we will continue to explore other consistency models, and specifically we will look into linearizability in leader-follower systems. And because in most of the real systems we have transactions, we will discuss how concept of transactions and concept of linearizability fits together. And because of real systems most often support transactions, we discuss how the concepts of transactions and linearizability fits together. We start with just brief description of linearizability, and the main point is that system behaves though there is a single data copy. Secondly, all operations, they follow some total order of operations, and this total order, unlike in sequential consistency, it follows real-time order. So if we have process A and process B, and process A executed some operation earlier in real time than process B, then when we merge them into the total order, this process A operation will be before process B operation in that specific order. Also, acknowledged writes are immediately visible for all future reads, and once a read sees some value, all future reads must also see the same value unless it was overwritten. Actually, I have another video which discusses different consistency models, and it has a very detailed explanation of linearizability. It goes down towards the very formal definition and explains it. And also it provides some easy to understand examples of what linearizability is and how it's compared to other consistency models. According to Martin Kleppmann, who is author of the famous book Designing Data-Intensive Applications, leader-follower replication system with synchronous followers is potentially linearizable. And he says that it's potentially linearizable because of multiple edge cases, design decisions, concurrency bugs, and so on. But he's not very specific here, and he just briefly mentions that something could go wrong and we need to be careful. And in this video, I just want to provide some more specific examples of when leader-follower system with synchronous follower might behave in non-linearizable way. First of all, it seems initially that system with synchronous follower is linearizable because we write something, it's synchronously getting replicated, and only after that there is acknowledgement of follower. So the first obvious things that could go wrong is configuration of the system which prioritizes performance over the consistency. And I have explained that in the first video of this series, and also it's available in my article, there are two problems of configuration. First is that sometimes writes might not be immediately visible even with synchronous followers. And secondly is that out-of-order writes are possible, even with synchronous followers. Those are not bugs, it's just a configuration which can be changed, and sometimes by default it's not compatible with linearizability. Secondly, of course, there are concurrency bugs, and thirdly, there is question of failover. When leader fail and we need to transfer the leadership role from leader to follower, and it has a lot of edge cases. Apart from that, there is a question of transactions, and transactions, they make things much more complex, and because most real systems, they have transactions, so let's see how linearizability and transactions fit together. And in fact, linearizability does not make much sense when it's applied to transactions directly. Because in linearizability, we say that operations have to become visible immediately after they were written. And with transactions, we say that operations must become visible only after they are committed. For example, with transactions, we can make 10 writes into the system, but they will not be visible. And they only will become visible after we executed commit statement. So this is a contradiction with linearizability, and if we apply definition of linearizability as is to transactional system, then such system would not be linearizable. But to apply the idea of linearizability to transactional systems, we need to modify the concept. We actually need to introduce another consistency model, which is called external consistency, or the other name is strict serializability. It's the strongest consistency model, which is even stronger than linearizability because it operates on transactions level. And here on the picture, I'll show the illustration of external consistency and how operations should be serialized to satisfy the external consistency under presence of transactions. Here we see the time flow and 3 transactions marked with different color, and each transaction has some operations marked as rectangles. So transaction A has 2 operations, transaction B has only 1 operation, and transaction C has 3 operations. And those bold circles, they mark the beginning of transaction and the end of transaction. And external consistency requires that in serial order all operations were ordered according to their commit timestamp. For example, here we see that the first transaction to end was transaction C. It was committed at the moment T1. And we require that in serial order all operations of that transaction were before operations of other 2 transactions. Then second committed operation was transaction A, and here are 2 operations of transaction A, and the last one is transaction B. So in system which supports external consistency or strict serializability, the result would be as if all operations were ordered in that way. And of course, they become visible only after commit statement. Now, when we introduced the concept of external consistency, let's see leader-follower system with single leader and transactions and see cases when this external consistency can be violated. First such example of violation of external consistency is a repeatable read or snapshot isolation. So when we have systems with transactions can be isolated one from another, and there could be different isolation levels, from the very low isolation when dirty reads are possible. For example, when one transaction made some write, but it's not yet committed, but other transaction can already see it. It's a very low isolation level. Until very strict isolation levels, when transactions just behave as though they were executed sequentially, which is called serializable. And there are some levels in between, and one of such isolation level is a repeatable read or snapshot isolation. And basically it says that when transaction starts, it should kind of make snapshot of all the data, and it should see only the changes which were made before transaction started. So kind of our transaction reads from snapshot of the data which was there before it started. And this snapshot isolation, it breaks linearizability and external consistency, and let's see why. So first, there are 4 transactions, and it's just an example of what transactions would see with snapshot isolation. Let's focus on transaction 3. As on previous example, those black circles, they mean either start of the transaction or commit of the transaction. And this transaction 3, when it starts, it's making snapshot for this transaction, and only transactions which were committed before this snapshot, they will be visible for this transaction. In our example, only transaction 1 has committed before transaction 3 started. So according to the rules of snapshot isolation, transaction 3 will see only this write made by transaction 1. But this violates both linearizability and external consistency. Linearizability is violated, for example, because of this write by transaction 2 and all of that other writes by transaction 4. For example, read number 4, it will not see any of those writes, though they were made in the system before that read is executed. So it's obvious that linearizability is violated. Now let's see the external consistency that takes transactions into account. And the external consistency says to us that if transaction was committed before our transaction, then all the writes made by this transaction must be visible in this transaction. And with snapshot isolation, it does not happen, because on the moment when its transaction started and snapshot was taken, this transaction was not yet committed. And because of this, those reads will not be able to see those writes, despite the fact that in serial order this transaction is committed first. So we see that sometimes just by the system design, by requirements to our isolation level, the consistency requirements of linearizability or external consistency will not be satisfied. And there is another example when they are not satisfied not by some conscious design decision, but because of some kind of side effect which is not very obvious at first glance. And we will consider Postgres, for example. And the case with Postgres, that transactions are ordered by internal transaction ID, TXID parameter. And this transaction ID in Postgres is assigned to transaction when the first statement in this transaction is executed and not by the commit time. And it means that it does not satisfy external consistency, because all transactions will be ordered according to their first statement instead of their commit. And let's see an example. Here I have used Postgres 14.5 and I had just two terminals and executed following commands, and you can see the commands and the output. So in the first session I have started the transaction in Postgres, then I started it in the second window. Next, in the second transaction, I do some insert into table comments. It doesn't matter what exactly is happening here. The important is that I did some insert operation. And here, transaction ID is assigned to this transaction. And after that, I do similar insert statement into the first transaction. Because of the order of the first operations in those transactions where that transaction 2 was first, it will get assigned smaller transaction ID, and we can verify it here. So we just check transaction ID of current transaction, and we see that for the first session we have 794. And for the second session we have transaction ID 793, and then we do the commits. And we see that this transaction started earlier than transaction 2. Also, it was committed earlier than transaction 2. But despite of that, it will get higher transaction ID, and this will get lower transaction ID. And considering that Postgres orders transactions according to their transaction ID, it's not externally consistent, because this schema will not be satisfied. So I just showed some examples how transactions add the complexity, and that in transactional systems you need to read the documentation even more carefully to understand consistency implications of this in specific real systems. The classic example of a system when we need strict consistency models like linearizability or external consistency is banking systems. For example, here is the system which supports deposits, withdrawals, transfers, balance check. And in such system, all write operations which change something, they go to the ledger, and operations of getting balance, they must go to synchronous follower. In such system, we have linearizability or strict consistency, and it's required, for example, not to overspend or to ensure that we transfer money from one account to another. We don't end up in some state when money is taken from one account but not delivered to another account during the operation. In such system, we also can use asynchronous followers, but for some flows which are not directly related to the transfers, to getting balance. For example, we could use it for reporting, analysis, for backups, and for something like that when we don't need strict consistency guarantees. And this concludes the series of videos about which consistency models we can achieve on leader-follower systems and how to do that, what are the implications, edge cases, examples, and how we can use them in real systems. I hope it was useful for you and you enjoyed it. If you have any questions or any ideas about future videos, or maybe if you don't understand some topic and would like to understand it, don't hesitate to contact me, and I can consider it during preparation of my new videos. Bye, and hope to see you again on my channel, so don't forget to subscribe not to miss any updates. Bye.